Welcome to 11.6 Convergent Geometric Series. Take a look at the warm-up. It says use your calculator to find the 4th partial sum, the 6th partial sum, the 10th partial sum, and the 20th partial sum. Then state whether the infinite series seems to converge, approach a single value. If yes, state the value. So we're going to use our calculators for this. So I want to jump over to a calculator page and remind you of a little tech tip that we talked about earlier in the year. So I went ahead and pre-entered the formula for the sum, the nth partial sum of a geometric series, and you'll notice that we have T1, which is 4, and then we have R, which is 0.5 in the warm-up A, and on the bottom you can see I did 1 minus 0.5, so I've got the first three results. So I have S4, S6, and S10. When you're doing this, you can save a little time by simply highlighting the entry and hit enter, and then go back in, and since the last one was 20, we can change that and quickly get the answer. Now look at the results. We started off with the first one, which was S4, 7.5, and we worked our way all the way up to 20 terms. We're barely increasing as we go, and it looks like it's hovering around 7.99. So a reasonable guess would be to say that this sum over time is going to approach 8 because it was barely increasing. Now if we move on to warm-up B, we'll notice that it too is geometric and the R value happens to be 2. So we're going to find the partial sums from 4 all the way up to 20. We're going to hop over to our calculator again, and I preloaded it for time. But what you'll notice is the 4th partial sum was 15, and working our way all the way down to the 20th partial sum, we're at 1,048,575. So it appears to be that it's constantly increasing. So the only thing we can say about this sum is that it doesn't converge, and we'd have to say this reasonable guess would be infinity. It's going to increase ever more as we go up. So the S sub n is called the nth partial sum if the sequence of the partial sums S1, S2, all the way to Sn has a finite limit S. Then the infinite series is said to converge to the sum of S. So in warm-up A, it converged to 8. If the sequence of partial sums approaches infinity or has no finite limit, then it's said to be divergent or diverge. So warm-up B, we would say it diverges. So let's talk about the summary. This is only for an infinite geometric series. You're adding up an infinite amount of terms. If the absolute value of R is less than 1, then the series is actually going to converge, and basically the formula becomes the sum of an infinite series is T1 over 1 minus R. If the absolute value of R is greater than or equal to 1, and T sub 1 is not equal to 0, then the series is going to diverge. So we showed you both examples. Now let's talk a little bit more about the shortened version of the formula from the previous days. So some notation that we kind of spoke about earlier in the year was limits. And if you haven't talked about that yet, that's okay. But limit notation, when you get to calculus, all this means is the limit as n approaches infinity. And we have our normal formula, T1 times quantity 1 minus R to the n, all over 1 minus R. Well, what happens is, as we move on, as n gets really large, think about it. If R is less than 1, if the absolute value of R is less than 1, and you're taking a small number to the nth power, it's going to be practically 0. So then you can see that 1 minus 0 is just 1, and then you end up getting the shortened version. So this only works when the absolute value of R is less than 1. Why is there not a theorem for the sum of an infinite arithmetic series? Well, think about it. Arithmetic sequences have a common difference. And that common difference is going to lead to the sum being infinity or negative infinity over time, because you have basically positive, sorry about that, so it would have a positive slope or a negative slope. So basically you're going to be adding all your terms on a positive slope or negative slope, which is going to create a divergent situation where your sum is going to be infinity or negative infinity. Let's look at example 1. Find the sum of the infinite geometric series, 9 minus 6 plus 4 minus dot dot dot. So in this problem, we recognize that r is equal to the second term divided by the first term, so it's going to be negative 2/3, because negative 6 divided by 9. And the sum, we can use the convergent sum formula because the absolute value of r is less than 1. The first term is 9. 1 minus negative 2/3. And so, doing the math, we get 27/5. Example 2. Find the first three terms of an infinite geometric sequence with sum 16 and common ratio of negative 1/2. So 16 is equal to the sum. We do not know t1, and we know that 1 minus negative 1/2 would be the bottom of the formula. So doing the math, we get 16 equals t1 over 1 plus 1/2, which is 1.5. And then I would multiply through by 1.5. And from there, I would get t1 equals 24. And it would be simple to find t2 because you just have to multiply by negative 1/2. So it's negative 12. And you could find t3 by multiplying negative 12 by negative 1/2, which would be 6. Example 3. What is the value of x if the series converges to 3/5? So they're telling you, by saying it, the word converge, they're telling you that the absolute value of r has to be less than 1. So we can use that to our advantage. Going up to the formula, we know 3/5 is the sum. We can tell that the first term is 1. 1 minus, and if we look at this, we look at the 2x is the second term of the sequence. So that means that r must be 2x. So now all we have to do is cross multiply. We're going to distribute the 3 onto the quantity 1 minus 2x to get 3 minus 6x equals 5 times 1 is 5. We're going to subtract 3, so negative 6x equals 2. And then we're going to divide by negative 6. So x is going to equal negative 1/3. Example 4. For what values of x does the following series converge? Again, use the word converge, so they're implying that the absolute value of r must be less than 1. So we can tell from looking at this that r is equal to x minus 2. Well, we know that the absolute value of r is less than 1, so that means that the absolute value of x minus 2 must be less than 1. Therefore, x minus 2 must be between negative 1 and 1. So we add 2 to both sides of the inequalities, and we get 1 is less than x, which is less than 3. This, by the way, is known as the interval of convergence. Any numbers between 1 and 3, non-inclusive, would yield a infinite sum that would be convergent. Let's look at example 5. So in example 5, we have a repeating decimal, but something that's required here is they want you to write it as a rational number. Now, one shortcut way is to enter this into your calculator as far off of the screen as you can, and then go to, I think it's number under menu, and then convert it to a fraction, and it usually works. But I want to show you the math behind this. If we split this up and make it a sequence, we have 0.45 plus 0.0045 plus 0.00045, etc. Well, that is a geometric sequence. R happens to be 0.01. So basically what you're doing is adding up an infinite amount of terms to get a repeating decimal. So knowing what we've learned today, we know that the sum is going to converge. The first term is 0.45. And we're going to do that of 1 minus r. R was 0.01. So when we get this, we get 0.45 over 0.99, which is basically 45 over 99. And that reduces to 5/11. That is your rational number for 0.45 repeating. Good luck on your homework.